This morning, we are going to look at development and congenital malformations of the digestive system. Otherwise, I hope you people are fine. We know that we've already looked at the gross anatomy of the digestive system. So this is basically the last part of the lecture series on the digestive system. The intention of this lecture is to first help us relook into the process of embryonic folding and state the effect that has on the yolk sac. I hope you do remember what the yolk sac was, and I hope you do remember how the embryo folds. After you've done that, we're going to outline the embryonic origin of the various tissues and organs of the digestive system. Then we'll talk about something called the primordial gut. We're going to name its parts, and we're going to see the derivatives of each part. After that, we'll then look at the development and congenital malformations of the different parts of the whole of GIT, starting from the esophagus all the way to the rectum. We'll then describe what we call the cloaca. We'll explain how it's partitioned and its derivatives and associated malformations. And lastly, we'll talk about the embryonic origins and malformations of the hepatobiliary system. So without further ado, we can start with the first agenda, which is to review the process of embryonic folding and to state what that has in terms of effect on the yolk sac. So just to remind you that the embryo folds in two planes. There's a transverse embryonic folding where the embryo folds in the lateral plane. We call that the lateral folding. And there is the folding of the embryo in the craniocaudal axis, which we call the sagittal folding. Let's look at how the embryo folds in the transverse axis first. I'm going to play two videos for you. The video on your left shows you the folding of the embryo in the transverse axis, and the video on your right will show you the process of embryonic folding in the craniocaudal axis. As we play the videos, I want you to take a keen attention on the effect of these processes on the yolk sac. If you do remember well, so a Trilamina embryo looks like this. Or let me give you a better view of that. So a Trilamina embryo looks like this, where we have the ectoderm, the blue layer, mesoderm, the middle layer there, and endoderm, the yellow layer. The green is an autocod, which induces the process of urulation which occurs on the ectoderm. Also, I want to note that the cavity next to the ectoderm side is the amniotic cavity. And the cavity next to the endoderm is the yolk sac cavity, also called the umbilical vesicle. So now we want to see how the embryo folds, and we can see how the folding process is going on. At this point, we see that the ectoderm is folding on itself to form a neurotube. Now, that is not part of embryonic folding per se. That is not what we are referring to when you're talking of the transverse embryonic folding. The folding of the ectoderm is aimed at forming the neural tube. So the process of neurulation is taking place at this point. We also note that at this point, the mesoderm has differentiated into three segments. the Paraxial Mesoderm, the Intermediate Mesoderm, and the Lateral Plate Mesoderm on this other side. And we can replicate that on the other side of the embryo as well. So at this point, the mesoderm has three segments: paraxial, intermediate, and lateral plate. A keen look at the lateral plate mesoderm also reveals to you that the lateral plate mesoderm is divided into two. The one above, which is next to the ectoderm, is known as the somatic layer of the lateral plate mesoderm. And the one below, next to the endoderm, is the splanchnic layer of the lateral plate mesoderm. You can as well just call them the somatic mesoderm and the splanchnic mesoderm. Now, so far, we've not seen a very characteristic event that is displaying the lateral folding, not yet. And so you've not seen any change so much on the amniotic sac and on the yolk sac, but now we are going to see. So let's follow that video now and see what happens. I want you to look at the yolk sac specifically at this point and see that the yolk sac is diminishing, it's becoming small, while the amniotic sac is expanding to surround the baby. Look at the shape of the baby now. The baby has become cylindrical. From that flat embryonic structure, the baby is now cylindrical. And yolk sac, some part of the yolk sac has been incorporated into the embryo. That part of the yolk sac that has been incorporated into the embryo is known as the embryonic gut tube, or that's the one we are going to form, called the primordial gut. Then there's a part of the yolk sac that is still outside. So this yolk sac that's outside is going to disappear pole-pole, not yet at this point. The connection between the two is known as the yolk stalk, or you may want to call it the vitelline duct. So that's the vitelline duct. This is the primordial gut, and this is the yolk sac that is degenerating. This is the baby, basically. The baby has become cylindrical now. So look at the layers of the Trilamina embryo that are surrounding the primordial gut. We can see endoderm is inside, followed by the splanchnic layer of the lateral plate mesoderm immediately outside. We will revisit this image in another static one shortly. But let's look at the process of embryonic folding in the sagittal plane and see what's new that maybe we've not seen yet. So in this video again, that's the amniotic sac, this is the yolk sac. This is what we call the allantois. You may not believe, but that's the heart developing, and this is the brain. You see at this point, the heart is actually cranial to the brain. But through this folding, we're going to see the heart descend down to the thorax. This is the chorionic plate. This is the chorionic cavity. Sorry, something has happened. The other video is the one that has moved, but let me handle that shortly. Okay, so we're on this, the one on your right. So we can see the parts of the embryo labeled there. You can see where the heart is, as I was telling you. Look at that. Look at how the heart is descending down to the thorax and how the brain now becomes cranial. But importantly, look at how the yolk sac is being incorporated into the baby, and some part of the yolk sac remaining outside. A narrow segment between the two. This part of the yolk sac that has been incorporated is the one we are calling the primordial gut, which is this one. This part of the yolk sac that is outside is the same as this one. It will disappear. This part here is the same as this other part, the vitelline duct. So these static images capture that storyline. And importantly, I want you to note that as the embryo falls, the dorsal part of the yolk sac become incorporated into the developing embryo. That's the message. And as the dorsal part become incorporated into the embryo, that dorsal part of the yolk sac will then become the primordial gut, the primary alimentary canal. And this primary alimentary canal is lined by two tissue layers. Inner layer is the endoderm layer, followed by the Splanclic Mesoderm immediately outside it. The primordial gut has three segments. The part of the primordial gut that is attached to the vitelline duct is called the midgut segment. The part of the primordial gut that is attached to the vitelline duct. So this segment here is called the midgut segment. The region of the primordial gut cranial to the midgut is called the foregut. So that's the one towards where the future mouth would be. And the region of the primordial gut caudal to the midgut is called the hindgut. That's the part towards where the future rectum and anal canal will be. So the primordial gut has three segments: foregut, midgut, and hindgut. Now we've looked at the embryonic folding, and we've stated its effect on the yolk sac, that when the embryo falls, the yolk sac become incorporated into the baby, and that will become the future alimentary canal. Now let's look at the embryonic origins of the different tissues and organs of the digestive system. We have stated that endoderm is the innermost layer of the primordial gut. And as the embryo falls, these two images show us different stages of embryonic folding. We can see this is the future alimentary canal. And in this image, we see it better than the yellow represents endoderm, the inner lining of the gut. So having mentioned that endoderm is the innermost layer of the gut wall, what does endoderm really become? The endoderm will form the epithelial lining of the alimentary canal. So epithelium of the esophagus, epithelium of the stomach, epithelium of the intestines will come from endoderm. Remember that epithelium varies depending on which part of the body you're in, which part of the GIT you are in, but it does not matter the type of the epithelium. All the epithelia of the GIT come from endoderm. Endoderm also gives us the exocrine glands of the digestive system. These glands can either be intrinsic or extrinsic, as we talked about them last 2 weeks or so. Whether they are intrinsic or extrinsic, the exocrine glands, exocrine organs of the digestive system arise from endoderm. They grow from endoderm as a diverticulum from the lumen. And that's why they still retain their duct into the lumen. Then we have the Splanclic Mesoderm. Again, from these images, you see this, the Splanclic Mesoderm, that one called visceral layer of the lateral plate mesoderm. That's the Splanclic Mesoderm, which we also see here. That's the Splanclic Mesoderm, very intimate with the endoderm that is forming the alimentary canal. And in these images, we capture that better. Splanclic mesoderm near the endoderm. And here we can see it surrounding the whole of the endoderm that forming the gut. What does splanclic mesoderm become? Splanclic mesoderm form the connective tissue elements of the digestive system. So think through where those connective tissue elements are found. Maybe it is part of the lamina propria. Maybe it's part of the submucosal layer. Or maybe it's part of the adventitia. All of them arise from splanclic mesoderm. Apart from the connective tissue elements, splanclic mesoderm also gives rise to the musculature of the gut wall, the smooth muscles of the gut wall. So remember, the muscular layer of the gut wall is predominantly formed of inner circular layer of muscles and outer longitudinal layer of muscles. Those layers of muscles arise from splanclic mesoderm. Lastly, the splanclic mesoderm also forms the mesentery of the intestines. The mesentery of the intestine is a membrane that suspends the intestines, and I showed you mesentery in our previous lectures. So it will be something that looks like this that also arises from the splanclic mesoderm. They're just regions where the two layers of the mesoderm have been interposed. The other entity of cells that give rise to different components, some components of the digestive system, are the neural crest cells. So you'll remember that when the neural plate undergoes neurulation, it will form the neurotubules. But there's some cells of the neural plate that are not incorporated into the tube. The cells of the neural plate which are not incorporated into the tube constitute the neural crest cells. The neural crest cells are very migratory, and they're also pluripotent cells. Migratory to mean they live where they are and move to other parts of the body. And pluripotent to mean that they have the capacity of forming multiple tissue lines. On that note, therefore, neural crest cells usually migrate and invade the developing alimentary canal. As they do so, they differentiate into nerves, which will be now within the wall of the GIT. Remember, the nerves which are in the wall of the GIT are known as the enteric nervous system. And that we have two components of the enteric nervous system, the myenteric plexus of nerves and the submucosal plexus of nerves. Both of them arise from the neural crest cells. You remember that the myenteric plexus is within the muscular wall, and that will control peristalsis. The submucosal plexus is within the submucosa, as the name suggests, and that would control secretions. Right, so that's where we are. We've talked about the embryonic origins of the different tissues and organs of the digestive system. We've seen three major embryonic tissues contributing to the development of the tissues and organs of the digestive system: endoderm, splanclic mesoderm, and neural crest cells. Now let's name the parts of the primordial gut, those segments of the primordial gut, and give the derivatives of each part. Let's start with the derivatives of the foregut. So this is the foregut from here all the way to somewhere there, actually. The whole of that is the foregut. Foregut tends to be a bit long. So what does foregut become? Foregut will give us some segments of the alimentary canal. The segments of the alimentary canal that come from the foregut extend from the pharynx all the way to the duodenum. So what does that mean? It means that foregut will give us the pharynx. It will also give us the esophagus. Then it will give rise to the stomach. And lastly, it gives rise to the proximal part of the duodenum. Usually the first and the second part of the duodenum are the ones we're talking about here. So the whole of that is the foregut and its derivatives. But the foregut does not just give us a component of the alimentary canal. Foregut also gives us extrinsic glands of the digestive system. The extrinsic glands of the digestive system that come from the foregut are the liver, the pancreas, and the biliary tree. So in this image we see, so perhaps this is the region that will give us the pharynx, then perhaps esophagus, stomach, then proximal part of the duodenum somewhere there, up to somewhere there, that's where the foregut ends. And that point corresponds with somewhere within the second part of the duodenum, what we call last time D2. So in addition to the hollow GIT, the foregut also gives rise to extrinsic glands of the digestive system, liver, pancreas, and the biliary tree. However, again, from your previous lectures, I am not so sure whether I'm the one who gave that, but you've had it, that foregut also gives rise to the lower respiratory system. This thing here we are seeing that's being called tracheobronchial diverticulum, the blue one, is also called the respiratory diverticulum. It is from that point where the lower respiratory tree comes from. And so the larynx, trachea, bronchi, and the lungs as a whole actually come from the anterior part of the foregut, corresponding with the region of the pharynx and esophagus there. Those are the foregut derivatives. I want you to remember that because when you're going to talk about malformations of the esophagus, then some of those malformations will be based on the fact that foregut does not just give you the digestive system, it also gives you the respiratory system. What are the midgut derivatives? So midgut is this region where the gut is attached to the vitelline duct. I forgot to tell you in the previous slide that the artery of the foregut is the celiac trunk, a branch of the aorta. When we come to the midgut, the artery of the midgut is the superior mesenteric artery, which is also a branch of the aorta. Superior mesenteric artery is a branch of the aorta. All right, so what does midgut give us? The midgut will give us a large part of the small intestine. So starting from the duodenum, which means it will give us the distal segments of the duodenum. So we are talking of D3 and D4, but we're also talking of a small part of D2, the distal part of D2. Because the junction between the foregut and the midgut is not exactly at the junction between D2 and D3, but somewhere in the lower part of D2. So midgut will give us the duodenum, the distal part of the duodenum. It will give us the whole of the jejunum and the whole of the ileum. And there are also some parts of the large gut which also come from the midgut. In this image, let's assume that the midgut is arising from somewhere here. So perhaps the D2 ended somewhere there. So maybe this segment give us D3 and D4. Then perhaps the jejunum and ileum. That region there that I've shown you, we call it the cephalic limb of the midgut loop, or cephalic limb of the primary intestinal loop. So the small gut comes from the cephalic limb of the primary intestinal loop. The junction between the cephalic limb and the caudal limb is this one, the position of the vitelline duct. So take home story, the small gut arises from the cephalic limb of the midgut. The large gut arises from the caudal limb of the midgut. But which part of the large gut actually comes from the caudal limb? So we have the cecum, we have the appendix, we have the ascending colon, and the transverse colon. For the transverse colon, it is not the whole of the transverse colon, but just the right side of the transverse colon, maybe a half to 3/4 from the right side. Remember, the artery of the midgut is a superior mesenteric artery. So from there, then we can talk about the hindgut. We would now expect the hindgut to give us the distal parts of the large gut, which means extending from the transverse colon, we will have the distal part of the transverse colon. Then we'll have the whole of the descending colon, and perhaps the whole of the sigmoid colon. So basically the colon, the left side of the colon, comes from the hindgut. Apart from the left colon, which comes from the hindgut, look at this. The hindgut has a common union with the allantois. The common union of the hindgut and the allantois is known as the cloaca. The cloaca is a common chamber connecting the allantois and the hindgut. As development continues in any mammal, the cloaca become partitioned into two, and we are going to see cloacal partitioning. When cloaca becomes partitioned, it will form two chambers, an anterior chamber and the posterior chamber. The posterior chamber is known as the Anorectal Canal. And as the name suggests, that's the part that gives us the anus and the rectum. So I'm mentioning the cloaca here because it's a continuation of the hindgut. But having said so, we've now given the parts of the primordial gut and the derivatives of each part of the primordial gut. Now we can address the fourth agenda, where we are going to look at development and associated malformations of the different parts of the alimentary canal. Let's start with the one of the esophagus. So we've said that esophagus arises from the foregut, but we've also said that the the foregut also gives rise to the respiratory tree. Usually, as development continues, the two systems will have to be separated by a septum. The foregut must undergo septation so that the respiratory tree is separated from the digestive tree at the level of the foregut. The feature structures which become, the structures which are formed from that kind of process are basically the trachea in front and the esophagus behind. If the process of foregut septation does not go on well, then we will have abnormal communications and connections between the trachea and the esophagus. And some of this will also be associated with blockage of the esophagus. The term given to blockage of the esophagus is esophageal atresia. The term given to the abdominal communication between the trachea and the esophagus is Tracheosophageal Fistula. Because they tend to occur as one entity, we give them that complex name. Although in practice, we just call them Tracheosophageal Fistula. There are different morphological types of Tracheosophageal Fistula, as you can see. In the first image there, which we call type A Tracheosophageal Fistula, actually there is no fistula. There is no abdominal connection between the esophagus and the trachea. But we can see that the esophagus is blocked at some point. This lack of tubular lumen continuity is what we are calling atresia. So type A TOF, TOF for Tracheosophageal Fistula. Type A TOF is esophageal atresia without Tracheosophageal Fistula. That may sound ambiguous. We are saying it's TOF, but we are saying there's no fistula again. But that's the ease that we want to put as we classify the TOFs. We are looking at them in terms of the entity of the malformation with different degrees of severity. Look at type 2, type B, TOF. So the esophageal lumen is not continuous. We can see the proximal and distal segment are not continuous. So we still use the term esophageal atresia there. There is esophageal atresia to mean that food cannot move from the mouth to the stomach through the esophagus. There's a point where there is no continuity. But in addition to the atresia, we also have a fistula. This fistula is involved in the proximal segment. As opposed to type C, where yes, there's atresia with a fistula that involves the distal segment. And type D, where there is atresia and fistula involving both proximal and distal segments. And then type E, where there is no atresia, but there is a fistula. So these are the different entities of tracheosophageal fistula. Type A, TOF, is esophageal atresia without tracheosophageal fistula. Type B, TOF, is esophageal atresia with proximal tracheosophageal fistula. Type C, TOF, is esophageal atresia with a distal tracheosophageal fistula. And type C is the commonest type. Type D, TOF, is esophageal atresia with both proximal and distal tracheosophageal fistulae. And type E, TOF, is tracheosophageal fistula without esophageal atresia. I want you to understand that there are different morphological types, but there's something else I want you to understand. I want you to figure out how this child in type C will present clinically, because this is the commonest type of TOF. We need to know how to capture it so that if a baby is born prematurely or maturely, whatever, and they have this kind of malformation, we're able to make a clinical diagnosis or a clinical suspicion of type C tracheosophageal fistula. So let me hear from you people. If you have an idea, just put up your hand and I will enable your mic. I have muted all of you because there's some noise I was hearing from the background. But if you have an idea, just raise your hand and I'll give you a chance to talk. Yes, I'll give it to Aquilin first. Yes, Aquilin, carry on.
I think the child will vomit.
All right, fair enough.
All right, fair enough.
So you are right that something will come out from the mouth of the child. I don't want us, though, to call that vomiting, because you vomit something that has reached the stomach. So this child will not be vomiting because the food will not have reached the stomach. The term that you'd have used is regurgitation of food, that when they try to swallow, the food just comes back. So that's the first one I want you to pick, that this child will regurgitate food. Apart from regurgitation of food, how else will this child present clinically? Any other person, just raise up your hand and I'll give you a chance. Apart from regurgitation of food, how else will this child present clinically? Remember, we are looking at the child in type C, the commonest type of TOF. Yes, Vivian?
The child won't have bowel activity.
Sorry?
No bowel activity.
Very good, that there'll be no bowel movements. You may not be able to hear the bowel movements when you put the stethoscope in the abdomen, because there's no food in the abdomen. So basically you may not hear the bowel movements. Very good. Anything else? Anyone? Try to keep it simple to your level of anatomy. The one for bowel movement is very clinical, but it's very true. Just based on what you see here. Okay, I'll ask you that same question another day in a different forum. You'll still answer it. Let's proceed. So here, we see an esophagus that has not gone down to the abdomen, a short esophagus. And because the esophagus is slightly short, the junction between the esophagus and the stomach is above the diaphragm. Usually the gastroesophageal junction should be below the diaphragm. So if the gastroesophageal junction is above the diaphragm, it means that there's some parts of the stomach which have gone through the diaphragm. We call that hiatal hernia. If you're born with it, then we give it the term congenital hiatal hernia. It means some part of the stomach protruding through the diaphragm to reach the thorax. In the last image, we see an esophagus that has a narrow lumen at some point. The term given to narrow lumen is stenosis. This stenosis may be caused by presence of some thin tissues, membranes, which we call webs. So you may have esophageal webs, which give us esophageal stenosis. All right, now let's talk about the ones of the stomach. The commonest malformation of the stomach that we are likely to come across is where the stomach is having a very thick pyloric sphincter. Remember, the stomach is also a derivative of the foregut on the lower part of the esophagus. The junction between the stomach and the duodenum is the pylorus. So that region there may have a very thick muscle. And if you have a very thickened pyloric muscle, what happens to the lumen? The lumen becomes very narrow and long. We call this hypertrophic pyloric stenosis. It's a very common condition of the stomach. Now, whether it is actually congenital or not may be a bit debatable, because when a child is born, they may not have this problem. But within the first 6 to 8 weeks after birth, we see this problem. We commonly diagnose pyloric stenosis in the 2nd month of life. And that makes us then question whether the child was actually born with it. Is it really congenital? We still put it here because a very common thing, and it's perhaps still developmental, and we see it in the neonatal period anyway. So let's just still call it congenital. Fine. Whatever it is, just know that it exists. How will this child present? This child will be vomiting, because now when food is in the stomach, it can't go through the pyloric canal. So what happens? The peristalsis of food, the peristalsis of the stomach, makes the pressure within the stomach to rise so high that food can easily pass through the cardiac sphincter to be vomited rather than pass through the pyloric sphincter to go to the duodenum. That does not mean that there's no food that goes down. Still there's food that goes, but these children vomit a lot. Now, the stomach also usually rotates. And as the stomach rotates, it takes its normal position, which should be that the fundus should be up and the pylorus down. The greater curvature should be on the left and the lesser curvature should be on the right. If the stomach does not rotate properly, it will give us this forms of stomach position. Look at where the esophagus is coming. So this is the cardia there, and this is the fundus of the stomach. When the fundus is below, we know that the stomach has not well rotated. So we just call it malrotation of the stomach. How about the one for the intestines? Before I take you through the malformations of the intestines, there's some things I want to say about the intestine in terms of their development. In terms of the site of origin, the intestines will come from the distal part of the foregut, which is the part responsible for giving us the duodenum, the proximal part of the duodenum. Then the whole of the midgut. And remember, the whole of the midgut gives us some part of the duodenum, the whole of the jejunum, the whole of the ileum. And the whole of the hindgut also gives us intestines. Because basically, okay, I didn't finish the story of the midgut. So apart from the small gut, the midgut also gives us the right side of the large gut. And then the hindgut gives us the left side of the hindgut. The hindgut gives us the left side of the large gut, which means that the whole of the intestines have now been accounted for, whether large or small, whether on the right or on the left, they come from this region, one of them. In terms of tissues of origin, we have indicated that endoderm gives you epithelial lining and glands. Splanclic Mesoderm gives you smooth musculature, connective tissue elements, and mesentery. And Crest gives us the enteric nervous system. In terms of the process of development, the intestines have some stages of development. First, the intestine proliferate very fast. And this is largely focusing on the region of the midgut. The midgut proliferates very fast. And if it proliferates fast, in as much as it was a short segment, it increases in length rapidly. So that rapid proliferation causes elongation. When the intestines elongate, increase in length, yet the two ends of the midgut are fixed, the midgut usually fold on itself. That should make sense, that if you increase the length but you don't adjust the ends, then the segment in the middle will fold. The first fold of the midgut is called the primary intestinal loop. And that's the loop that had the cephalic limb giving us the small gut and the caudal limb giving us the large gut. Something very important in embryology, something very phenomenal, something almost unbelievable, is that as the intestines develop, it reaches a point that they want enough space, but that space is not available within the abdomen of the fetus because the fetus is very small at this time. And so the fetal abdomen is really contracted. Apart from the contraction, the small nature of the fetal abdomen, there are some organs which are also competing with this space. We will see from next week that the renal system competes really with this space so significantly during development. Also, apart from renal system, the liver is also very big at this stage because the liver is the one that is one of the organs that is forming blood for the fetus at this stage. So it's also very prominent. I'm trying to say that there are some organs which compete even for the small space of the fetal abdomen. The liver and the kidney systems, together with the intestines, they compete. Yet this abdomen is also very small. So what usually happens? The intestines begin to do the unthinkable. The fetal intestines leave the abdomen, go through the umbilicus to outside the body. That process is what we call physiological umbilical herniation. The intestines herniate. They come from the abdomen, they go through the intestines, they pop through the intestines up to outside the body. The intention is to continue to develop outside the body, to continue to increase in length where there is enough space. When the intestines are doing that, they rotate 90 degrees in the anti-clockwise direction, so that what was down, what was on the rectal side, the segments of the intestines which were down basically go to the left, and the parts which were up go to the right. It is 90 degrees. While the intestines are outside the body within the hernia sac, they continue to develop. During that time, the vitelline duct disappears. The process of herniation takes place at the 6th week of gestation. And it is reversed between the 10th and 12th week of gestation. The intestines go back around the 10th to 12th week of gestation. As they go back, usually the duodenum is the one that will go back first, then the jejunum, then the ileum, in that order. As the intestines go back, the intestines rotate another 180 degrees in the anti-clockwise direction. Having mentioned that the duodenum began the journey going back, and then the jejunum, then ileum, it means that the small gut is less affected by this second rotation, but the large gut is significantly affected by this rotation. So remember, the large gut is the one that was below on the lower sides, the one near the rectum. During the 90 degrees anti-clockwise rotation, the large gut went to the left. So the large gut is on the left when the intestines are out in the sac. When the intestines going back, the intestines rotate 180 degrees, still in the anti-clockwise direction. So the large gut go up, then to the right. It explains to you why the colon takes that outline in your abdomen. If you are to follow the colon from the rectum side, how does the colon go? So from below to go to the left, sigmoid colon, then descending colon, then go up, transverse colon, then go to the right, the ascending colon, cecum, and appendix. That outline is because of how the large gut rotated during development. Now, to ensure that the intestines cannot come out again, because they did during development, the intestines must be fixed. Fixation of the intestines mean the loss of the mesentery. There's some parts of the intestine that lose their mesentery. The parts of the intestine that lose their mesentery are basically the ascending colon, the descending colon, and the duodenum. So those three parts lose their mesentery. So that now they're the ones which are being used to hold the intestines onto the abdomen so that the intestines cannot come out again. So that is the process of development of the intestines. I took you through that so that we can now easily understand the congenital anomalies of the intestines. So what are some of these congenital malformations? Look at that one. In this one, we see intestines which are within a hernia sac. We call it omphalocele. Perhaps the reason here is the physiological hernia was not reduced. I mean, the intestines herniated and didn't go back. Don't confuse that with this one, which we call gastroschisis. In gastroschisis, the problem is that there was a weak point, there was a defect, on the anterior abdominal wall. And so the intestines pop out through that defect. It's like you right now, if God forbid, if you have a spear through your abdomen, a deep one and a large one, the intestines can pop out. The intestines will not pop out because they are the ones with the problem. They'll be popping out because they're the ones near the defect. And that's the situation with the gastroschisis. In the first one, omphalocele, the intestines are the problem. They didn't go back after coming out. In the second one, there was a defect in the abdomen, and so the intestines popped out. How do you distinguish the two? At face value, you can see that the gastroschisis is not covered by a membrane, yet omphalocele is covered by a membrane. The other difference is that omphalocele will tend to be a midline problem. It's a midline defect. It is through the umbilicus. Gastroschisis is usually paramedian issue. It is usually on the right of the midline most of the time. This one is a bit common. I won't be surprised if one of you has this one. We call it umbilical hernia. Not quite a problem of the intestines again. It is because we have a defect in the umbilicus. And so abdominal content can pop out through that defect easily. We call that umbilical hernia. You may have abnormal rotation of the intestines, and that's what we call malrotation of the gut. Because the rotation largely affects the midgut, we just call it midgut malrotation. In midgut malrotation, how will you know? Usually the small gut will be on the right side and the large gut on the left side, as opposed to the small gut being central in the abdomen and the large gut being peripheral in the abdomen, as we agreed from our gross anatomy lectures. You see, like here, you expect the large gut to be peripheral and the small gut to be central. So that's the normal one. So if you have large gut on the left and a small gut on the right, it means there's a problem with the rotation. Perhaps the large gut did not do the total 270 degrees, 90 plus 180. Now, another anomaly that I want to talk about is what we call a ganglionic megacolon. So in a ganglionic megacolon, there's a problem with migration of the neurocrest cells. The neurocrest cells migrate into the GIT that's developing as we indicated, and this gives rise to the enteric nervous system. If the neurocrest cells do not migrate up to the lower end, so assume that the rectum and the sigmoid colon do not have the nerves, what happens? If the rectum and the sigmoid colon don't have the neurocrest cells, they don't have the nerves, those two segments cannot coordinate peristalsis. So what will happen when this child eats? The child will eat, food will go, but when it reaches the last normal segment, food cannot go beyond the last normal segment because the distal segment doesn't have peristalsis. So food cannot move through that. So what happens with time? That last normal segment will balloon out. And that's why we call it megacolon. It will distend. And this child will then present with abdominal distension. And remember that it's not going, the content's not going down. So they'll present with abdominal distension, but they'll also present with inability to pass stool. They may not have passed even the first stool, which we call meconium. They will not have passed meconium. So basically, we call it a ganglionic because there's a region of the gut that does not have the ganglion cells, the nerve cell bodies. That's why we call it a ganglionic megacolon. We call it congenital ganglionic megacolon, otherwise known as Hirschsprung's disease. And the other anomaly I want to highlight, which you shouldn't really forget in any anomaly, is atresia, means blocked. You can have atresia of any part of the GIT. We mentioned esophageal atresia, yes, but you can still have gastric atresia. You can have duodenal atresia, jejunal atresia, ileal atresia, colonic atresia, anal atresia. Atresia is lack of the tubular lumen continuity. You may also have duplication when you have parallel lumen. And if the vitelline duct persists, I hope you do remember from our previous lectures that if the vitelline duct persists, was it our previous lecture? Maybe not, but someone else must have taught you that if the vitelline duct persists, then you get what we call vitelline duct malformations. There are different spectra of vitelline duct malformations. This one is called the vitelline duct fistula, where the child will leak intestinal contents through the umbilicus. This is called Merkel's diverticulum, but this one is called fibrous cord. This is fibrous cord, and this is the vitelline duct sinus. This is fibrous cord, this is fibrous cord, this is vitelline duct cyst. So you may have Merkel's diverticulum, which you see there, or that one, that's still Merkel's diverticulum. That is vitelline duct fistula, vitelline duct cyst, vitelline duct sinus, on this end and fibrous cord that one. Okay, now let's talk about cloacal partitioning. Told you that the cloaca is a common union for the allantois and the hindgut. In mammals, the cloaca is partitioned by formation of a septum in the coronal plane that divide the cloaca into two. Anterior part is called the urogenital sinus, and the posterior part is called the anorectal canal. After the cloaca has been partitioned into those two, the urogenital sinus gives rise to the derivatives of the urinary and reproductive system. As the name suggests, we will revisit that later. But one of those would be the bladder and perhaps even the urethra. Even the vagina could be part of that. Then the posterior part is called the anorectal canal, which gives rise to the anus down here and the rectum up there. So based on that, we can then have some malformations of the cloaca. Look at this child, there's no anal opening. So just call that anal atresia. You can call it imperforate anus. You still see it there, the rectum and the anus not in continuity. So that's anal atresia or imperforate anus. This child cannot pass stool. You may have isolated anal atresia, but you may also have anal atresia with some fistulae. So these images show you anal atresia with some fistulae. Because in the first image I've shown you, stool has nowhere to go. There's anal atresia and stool has nowhere to go. But you may also have anal atresia, but stool has somewhere to go. So when stool has somewhere to go, it means there's a fistula. Where will the fistula be? In the first image, with a male child, there is anal atresia, but the stool is going to the urethra. So we call it anal atresia with urorectal fistula. Uro for urinary. On the second one, which is a girl child, there is anal atresia, but the stool is going to the vagina. So we call it anal atresia with the rectovaginal fistula. This girl child will be leaking stool through the vagina. This boy child will be leaking stool through urine. The extreme of cloacal malformation is what we call cloacal extrophy, where the cloaca is not partitioned, then it develops some abnormal tissue that protrudes out in the manner you're seeing in these fields. We call that cloacal extrophy. I know you're tired, but let's finish with the hepatobiliary system. So the hepatobiliary system, we are referring to the liver, the pancreas, and the biliary tree. As we indicated earlier, they arise from the foregut. The endoderm of the foregut is the one that gives rise to the hepatobiliary system. Initially, for the liver and gallbladder, initially there's a structure which we call the hepatic diverticulum that developed from the anterior aspect of the foregut. This hepatic diverticulum then divides into two. This part here, which we call the pars hepatica, which will give rise to the liver and some parts of the biliary tree. And this part here, which we call the pars cystica, P-A-R-S, pars cystica, which will give rise to the gallbladder and the cystic duct. The common stem of the hepatic diverticulum is the one that will become the common bile duct. So this is common bile duct. This is gallbladder and cystic duct. This is perhaps the common hepatic duct, right and left hepatic duct, and the liver itself. How about the pancreas? The pancreas developed from two buds. There's a dorsal pancreatic bud and a ventral pancreatic bud. So the ventral pancreatic bud usually rotates to join the dorsal pancreatic bud to eventually give rise to the pancreas. Now we can talk about the anomalies of the hepatobiliary system. The commonest anomalies that I want to highlight to you, the one you're seeing on your left, the first one, where we have some cysts along the biliary tree, we call them choledochal cysts. These are the commonest malformations of the biliary system, choledochal cysts. They're just cystic dilatations of the biliary tree, extrahepatic biliary tree for that matter. Then we have situations where the biliary tree may be collapsed or atretic. So we call that biliary atresia. So you don't have bile channels, basically. There is no gallbladder, or it is atretic. The common bile duct is atretic. We call it biliary atresia. A very bad malformation if you think about it. You may also have cystic dilatations of the biliary tree within the liver itself, like this one here in type 5 that you're seeing there. That type 5 choledochal cyst has a unique name. We call it Caroli's disease. When you have intrahepatic bile duct dilatations, we call it Caroli's disease. So these ones affect the biliary system. How about the ones that affect the pancreas? I'll teach you two congenital anomalies of the pancreas. One of them is where the ventral bud did not rotate well, and so it encircled the duodenum in its attempt to attach with the dorsal bud. So when it encircles the duodenum, it will cause narrowing of the duodenum, and we call that annular pancreas. So annular pancreas is pancreas that has surrounded the duodenum. And then we have what we call pancreas divisum. This happens when the dorsal and the ventral bud don't join their ducts. The ducts of the two don't join. So the pancreas is draining by two separate ducts, but interestingly, the large duct, the one of the dorsal bud, the main pancreatic duct, now is not draining to where the major duodenal papilla should be. The main pancreatic duct does not drain into the ampulla of Vater. It is draining into another minor papilla. That's what we call pancreas divisum. Great, so that summarizes the story that I wanted to share with you this morning on development and congenital malformations of the digestive system. I had purpose to finish it, and I've finished it. I'll invite you for questions if you have now.